for organizing this webinar on the software, which name in Italian, I use the Italian version of the name, is kSEMAW. Secondly, I would like to point out that I am a physicist and not a computer scientist. I have always written software in the wake of emergency, making use of guides, tutorial, and so on. kSEMAW has a long history. I began to develop what today is kSEMAW about 35 years ago. So it's very, very long time ago. For me, kSEMAW has been a sort of swift knife. I use it along my working life, always focused on the optical characterization of materials and devices. My working career in ENEA basically crossed three different fields: thin films, high energy physics, and optics of solar concentrators. In all these fields, I always use kSEMAW, that is grow during my my life. Okay, of course I developed many other software, but I never stopped to work on kSEMAW. And probably I invested some years of work in this software. Initially, kSEMAW was written in Fortran with command line interface. About 10 years ago, I added a graphical user interface written in C++ based on Qt library, who talked with the Fortran executable by text file. Then with the COVID pandemic, I totally rewrote kSEMAW in C++. So let's go to the meaning of the name. Except the first and the last letter, SEMAW is the acronym of Spectrophotometric, Ellipsometric, and Photothermal Deflection Spectroscopy Measurement Analysis Workbench. The first letter K stands for the use of Qt libraries. This is of use in Linux world. This is a symbol, just a symbol. The last letter C stands for the full C++ language that actually is used. This presentation is articulated in three parts. In the first, what is kSEMAW intended for? Then I will give you some details, and in the end, just some indication how to use it. Okay, kSEMAW deals with optical devices composed by layers from 1 to 9. Actually, 9 is the maximum number, but Alberto Mittiga is pushing me to increase this number because 9 for photovoltaic is not enough. These layers are composed by homogeneous or not materials, thin or thick, thin respect to the coherence length of the radiation. The interfaces of this layer are plane and parallel, but eventually with moderate roughness. Moderate means that the standard deviation have to be less of the wavelength of the radiation. What can kSEMAW do? kSEMAW can simulate spectrophotometric, ellipsometric, and photothermal deflection spectra. Can calculate the complex refractive index and thickness of a given thin layer when the surrounding layer are known. kSEMAW can evaluate the mean value of transmittance or reflectance weighted on a given international or customized spectrum. kSEMAW can predict transmittance and reflectance once a realistic or an equivalent model of the optical device has been set. In this class is now recently is we included the prediction of the absorbance in each layer. This is very important for you that work in photovoltaic. Here are some details. The language. Since version 1, the software is full written in C++. The graphical user interface is based on a Qt library. The plots are based on QVT library. And the nonlinear least square is based on a C++ version of the MIMPAC library. And in particular, we use the Levenberg-Marquardt nonlinear algorithm. The software is distributed as open source under the GNU version 3 licenses. You can download the software at this site. If you go there, you see this page. To download the software, you have to push the green button, and you will download a zip file containing all these files. Please note that here there are several important files for you. The last is the manual, the user manual. Here you have the last version of our paper published on Open Research Europe of the software of the kSEMAW, where you can find some application, some example of the use. And the most important thing is the workspace directory. The workspace, here I split a bit in deep. You can see it consists of source files, configuration files, exemplary data files, as well as the Microsoft Windows executable. And as I already said, there is the Microsoft Windows launcher. Concerning the installation, basically you have two options. The first option is the compilation of the source files. You can use Linux, Microsoft Windows, and Mac, but Mac is never tested till now. The installation is Linux. Under Linux, it's very easy, because actually today every Linux distribution has a package manager. So you just to set what package, what library you want to install, and the manager will do the work for you. The installation under Microsoft Windows is very tricky, and Alberto Mittiga spent a lot of time to get this goal. In particular, you have to install before the MinGV software, and then in any case you have to install this library, Qt, QVT, and the C++ version of MIMPAC. Then you have to launch the Qt Creator application. It is an integrated desktop environment for Qt application, and you have to load this file, kSEMAW.c.pro. This is the project, and then run the compilation. The second option is only for Microsoft Windows user, but maybe the most of you are Microsoft Windows user. And in this case, you have just to download the software, unzip in some part of your disk, and then you simply click on the launcher, and you will obtain the software running. Please note this important point, that kSEMAW, the software, works embedded in the workspace folder. because there are several configuration files in it. Another important point is you should understand that the philosophy is used in kSEMAW. That is, the kSEMAW is a software for the characterization of a physical device. Okay, so of course you generally do several measurements of this device. Okay, all data files concerning a given optical device should be named with a Unicode, adding suitable extensions. For the extension, I invite you to see the manual. Okay, another point is that since version 1, kSEMAW offers 3 different approaches for the evaluating of the unknown complex refractive index. We have the exhaustive numerical search, the standard fit method, and the hybrid one method. The hybrid one is in Italian is ibridone, means big hybrid, basically. Okay, when you launch the software, 2 windows will pop up. On the right, we have a terminal. The terminal is important because just to follow the workflow of the software. So if you experience a problem, some difficulties, you have to read the message, what is occurring. But for the user, normal user is enough. The graphical user interface on the left. This graphical user interface is organized in 6 tabs, which are ordered according to the workflow. The first tab is the Valin. Then we have the model, the simulation, the numerical search, the data fit, and then the graph range. Here on the right, you can see the Valin tab, where you can set which refractive index file have to be loaded in the software, in this part. While in this part, you have to select the name of the specimen, and then you can select which kind of measure you want to load, you want to consider in the analysis. Okay. In the model tab, of course, you have to set the optical model of your device. The model can be composed by layers. The maximum number of layers actually is 9. In this case, we have just 2 layers, and for each layer to have to specify which kind of layer is, if a bulk, if an homogeneous film, or is in inhomogeneous film. This is a graded index thin film. In this example, we have an inhomogeneous film on a bulk. Here you can see the thickness. In the phase for the thin film is angstrom, and for the bulk, these are millimeters. In this part of the graphical user interface, you have to set the materials you want to use. The material -1 is the unknown materials with the unknown refractive index. In this case, material 2 is set as the refractive index of the glass used as the substrate of this device. You see, it's set as material 2, and material 2 is set to the bulk, while material 1 is set to the layer thin film, and so on. Maybe this is a bit tricky, the use of the material, but in this way you can consider, we also consider a material composed by 2 different materials combined together according to the equivalent medium approximation. Okay, here we have the simulation tab. Here you can compare the simulated spectra with the experimental ones. But to do that, you have to set which is the unknown refractive index. And you can choose in this part of the graphical user interface, or like a constant value. Constant means not depending on the wavelength, or you can use a fit option, or you can use a refractive index file previously loaded in the Valin, or the value and the kappa value calculated in the software. Here we are using, in this example, we are using the fit option 1, which is composed by 3 different oscillators. A quantistic common, another quantistic homogeneous oscillator, and a flat term. Later, Alberto will explain you the different kind of oscillator kSEMAW has. In this tab, you can access to several actions. You can plot the experimental spectra. You can plot the simulated spectra. You can set the weights for computing mean values. You can plot mean values versus the incident angle, or this is maybe one of the most interesting for you, for the photovoltaic world, is the plot of the absorptance at each layer. Here you can see an example. We are always in simulation. We have plotted the experimental spectrum. These are the black curves. Here we have the transmittance and reflectance plotted versus the photon energy. Here we have the real part of the refractive index. And here is the excision coefficient, the logarithm. And these computed curves are calculated with this fit option, composed by 3 terms again, but here in this case we have an indirect gap Cody, a Drude term, and a flat term. The next tab is the numerical search. Here you can search solution in the NK space. This is in the space of the real and imaginary part of the refractive index at a given wavelength. In this case, we have loaded one transmittance, one reflectance, and if we run the research in the NK space, we obtain this graph, where the blue curves are this NK solution for the transmittance. The green curves are the solution for the reflectance. The cross-section is the common solution for transmittance and reflectance. This graph, this search, this kind of search is important if you even also to check if the combination of experimental measures we have set are enough independent to evaluate the unknown refractive index. The other possibility is to launch the exhaustive numerical search, and this is the results. You can see the results. This is the refractive index, the real part of the refractive index versus the photon energy, and this is the excision coefficient. Please note that the solution here we have, in this example, we are considering an ITO film on glass. The film is thin, and so the solution are grouped according branches. And you can see you have multiple solutions. And you can, you see, there is some crossing about this branch of solution, and as explained in the manual and the several papers, you can use this crossing to optimize the optical model, because when the model is set well, the crossings are well connected. You can pass with good continuity to obtain you can individuate the physical solution, and we can exclude these others that are just mathematical solution. Okay, here there is the data fit tab. Here there are several actions you can do. You can fit the real part of the data, maybe the data obtained by the exhaustive numerical search, for instance, as well as you can fit both real and imaginary part of the refractive index. Or you prefer, or if you prefer, you can fit the permittivity, epsilon 1, epsilon 2, or otherwise you can fit directly the experimental spectra like transmittance and reflectance, or the ellipsometric angle. Or the last option is to launch the hybrid one method. This method is original and is based on the fit of the reflectance spectrum. Once is a base model for the real part of the refractive index, you see. So you have to set a fit option composed by several oscillators, and you have to set the value of the parameters. Then, according to the hybrid one method, the imaginary part is numerically computed to obtain the given value of the transmittance. Then, altogether is called by the Levenberg-Marquardt minimization, and so you can, launching hybrid one, you can optimize the parameter of the used for modeling the real part of the refractive index, as well as the thickness of the layer, or for instance, in this case, is the gradient of the refractive index in the thin film, or this is the curvature in the always in the refractive index. Here is an example. You see in the blue are the solution obtained by the exhaustive numerical search. The red curves is the solution obtained by the hybrid one method. You can see that the transmittance, by definition, is perfectly reproduced by the hybrid one method. The reflectance here is not completely well modeled. It needs some improvement. Okay, finally, we have the graph range tab, where you can set the scale of the plot, the XY range of the plot. You can also set, if you want, the plot in energy or in wavelength in the abscissa, or if you want to use the logarithmic scale for the excision coefficient. And another interesting point here, you can set the font type at the sides of the character used for the graphical user interface. And this is very useful to optimize the look in your computer. Okay, how can you help? How can you help us in kSEMAW? You can become a beta tester. You can testing the software and reporting bugs, but you can also propose improvement to make the graphical user interface and the usage clearer, or asking for new feature, possibly of general relevance. If you are a computer expert, you could test the installation starting from the source, or another point, another weak point actually, probably is the code structure. It probably is not the optimal one. Okay, at this version of kSEMAW, kSEMAW starts with as a main personal work, but along the way, Alberto Mittiga did lots of work improving the optical constant model, but also in the Windows porting of the software, as well as in the drafting of the manual. Enrico Nichelatti, which is another colleague of us, is his support for the analytic for the search of analytical solution of the integrals of the density of the states, as well as for the manual, for the writing in LaTeX of the manual. Claudia Malerba and Francesca Minchini to be the alpha tester. Francesco Biccari for several useful suggestions for simplifying the software distribution. And finally, Luca Serenelli for his support in outlining the Linux installation procedure. Okay, this is the end of my presentation, and now Alberto Mittiga will show you, explain you the oscillator. Thank you.
Thank you, Alberto, very much.